G'day, I'm James, and welcome to Are All U-Shaped Graphs Quadratic? One of the first graphs one learns in school that's not a straight line graph is the graph of this one and all its friends. The graph is something like y equals x squared and its variations, because they lead to some sort of U-shaped graphs like this. And they're not straight lines. So this is the first time one sees something that's not a straight line, finally in school. Now let me be very clear, what do we mean by graph? The graph of an equation. So here's an equation. It's an equation about two numbers, y equals x squared, but no one's telling you which numbers to choose for x and for y. So what you do is you collect data for that equation, and the data is all the values that give true number sentences. Now you tend to be organized at first. You might make a little table, and you say, okay, maybe I can choose x equals 2 and x equals 4, and actually if I do that, I get a true sentence. 4 equals 2 squared. True. Beautiful. So there's a data point to go with that equation. And in fact, you can plot that data point by drawing some axes, x and y axes, and maybe you go say at 2, I want to go 4 high, gives me a point there at 4 high on the y-axis. Bingo, I've just got a visual representation of that data point. Another data point you might try is say x is 3 and y is 7. Well, if you try it, you'll get that 7 equals 3 squared. Not true, not a true number sentence. Since mathematics tends to focus on truth, you wouldn't bother collecting that data point for that equation. Then you probably choose 3 and 9 instead. And off you go, find that's true, 9 equals 3 squared, yep, you get a point up here, 9 high. Gorgeous. In fact, you do this and you get lots of points. Do 10 points, do 50 points, do 1,000 points, do 10 gazillion points, and eventually you'll start to see a beautiful curve emerge, and it looks like this. And it's symmetrical because it makes sense, because with 2 and 4, you could also do its matching point over here with -2 and 4 again over here, because 4 equals -2 squared as well. Symmetrical. 9 equals -3 squared as well. Symmetrical. In fact, you can find all the points here have a lovely symmetry about them, about that middle line there, that vertical axis down the middle. Great, so you get a symmetrical curve. In fact, I even call it a U-shaped graph. Many people call it U-shaped. But think about it, is that actually the correct term? Because if you draw the letter U, one tends to draw vertical sides on the letter U. So here's my question. Are these sides actually vertical? Do they ever become vertical? Well, if you think about it for a while, the answer is no. For example, if it's vertical at 3, that means my graph never goes beyond the number 3. But clearly I can put in x equals 4 and y equals 16, because 16 equals 4 squared is a valid data point, gives me a true number sentence. So there is a place for 4 at 16. There's a place for 5 at 25. There's a place for 100 at 100 squared. There's a place for 10 million at 10 million squared. This graph must actually keep spreading out. It can never be vertical. So even though I'll say, and many people do say as well, U-shaped graph, they really mean a graph that keeps spreading out in this kind of general U-shaped sense. Beautiful. So it's a symmetrical U-shaped graph. And these graphs are actually beautifully mysterious and strange and appear in all sorts of places in nature, which is what we'll explore in this particular experience today. But actually, here's my first question before we move on to the more serious work. If this graph keeps spreading out, is it so spread out that if I did the following, which is namely, take my blue curve here, if I just tilt the whole thing a small amount, say 0.1 degrees, I'll rotate about the origin, just a tiny angle of 0.01 degrees. So it just moves over. So this new graph in purple that's just moved over 0.01 degrees. So slightly tilted. So here's my question. Will this vertical axis and this tilted graph ever meet? Ooh, or is this graph so spread out that it'll just keep spreading out and still not meet the y-axis? That's a very good question. It's a deep question, seems very tricky and hard at first. In fact, look at the notes below this video that go with this lesson. I've got some thoughts to help you out on how to think about that one. All right, so lots of good things to think about. So it's not really U-shaped, they do spread out, but then something curious goes on for this situation. But let me now show you the truly miraculous thing about these quadratic graphs, but I need to give myself a bit more space. So let me clean the board and I'll be right back. Okay, now for a mind-blowing question about these quadratic equations is this one. Here's my example. We've got y equals x squared, the symmetrical U-shaped graph that we've just seen. But on this side it goes up and positive, and has a matching up and positive on the other side as well. Beautifully symmetric about that y-axis. And let me take another graph like y equals 2x. Now that's a straight line graph, you've probably been able to do that one from past years. And in some sense, it's kind of anti-symmetrical. When it's positive on this side, its matching point on the other side is the complete opposite direction. What goes positive here is negative there. Positive there, anti-positive there. Positive there, anti-positive there. So this is kind of like anti-symmetrical. I am wondering, and this is a vague question, I'm not sure if it really makes sense, what if I take this graph and add them together? What do I get? Equals what? Now, what do I mean possibly by adding together two graphs? Well, what I could do is the following. For example, I could take one point, like this point 1, which I know is going to be 1 high on my y equals x squared graph. And I'll take the point 1 here, which I know is going to be 2 high on the y equals 2x graph. So the point 1, I'll just add these heights. A height of 1 plus a height of 2 gives me a height of 3. So at the point 1, I'll now get a height of 3. I'll be up there. And the next point will be some positive height plus another positive height. So at 2, it'll be even another positive height. At 3, it'll be some positive height plus another positive height, positive height. So it's kind of clear the graph will be becoming big and positive onto the right. Now maybe it's a straight line up, maybe it's like curved, maybe it's curved, who knows what it's doing, but I can see it's going to be up and positive on the right. In fact, right at 0, now I've got a height of 0 there. At 0, I've got a height of 0. So a height of 0 plus a height of 0 at 0 is still being a height of 0. So actually, you can say the graph really goes from the origin up and positive. Now my details are very scary there, very sketchy. Maybe I could get that more sorted out as I do more refined thinking. But actually, the really interesting part is going to be on the negative side, the left side, because look what happens. On the left side, I'll be adding a positive number plus a negative number. So maybe the positive and negatives cancel out, and my graph is just flat 0 on the negative side. Or maybe the positives win, the positives are always bigger than the negatives, so it always stays slightly positive. Or maybe the negatives win, maybe it's more negative than it is positive and stays slightly negative. So this is very interesting. I'm wondering then, what is the graph of this graph, x squared, plus this graph, 2x. I want those y values to be added together, those two heights to be added together. So you look at this, and there's no reason you'd expect anything nice to come of this. I mean, this is my guesses, and they're really bad. Look how messy. But I know, if you studied a quadratics course, you know what the answer is meant to be, and it is shocking. If you really pause and think about it, it's absolutely shocking. Because I'm going to give it away right now. One learns in a quadratics class that actually, whenever you take a quadratic equation and you add a linear equation, a line to it, out comes another beautiful symmetrical U-shaped graph. Now it might be moved around a bit, it might be shifted on the plane, it might be shifted up and down, it might be made broader or thinner, it might be turned upside down. Who knows what's happened to it, but in the end, it's going to be another beautiful U-shaped graph. In fact, this one turns out to go through 0 and -1 on the x-axis. That is mind-blowing. Absolutely stunning. And I wish quadratic courses would make that really clear how mind-blowing that is. In general, y equals ax squared plus bx plus c is one of these U-shaped graphs plus a straight line graph, and out comes another symmetrical U-shaped graph? Wow. Wow, indeed. So this is why people are fascinated by quadratic equations, because they seem to be so incredibly robust. You can take a basic quadratic equation and add a line to it in this weird anti-symmetrical sense. Doesn't matter, it's still going to be a symmetrical U-shaped graph. That is wonderful and makes them so fascinating mathematically. But the other thing is, they also appear in nature all the time. For example, Galileo in the 1500s wondered about projectile motion, and he managed to prove, and we'll show it too as well, that this graph here that you get from watching a ball, it goes flying through the sky, turns out to be, in ideal conditions, another quadratic graph. Happens to be an upside down one, great, that is quadratic. Which then makes you wonder, well, are all U-shaped graphs I see in nature quadratic? For example, Galileo also wondered about this one. I've got a hanging chain here. It definitely looks like it could be quadratic. Is it? How do I know? How do I figure it out? Also, the Greeks, way back 2,000 years ago, played with geometry, and they discovered this graph here called a parabola. It has a lovely geometric property that each point on the parabola, its distance from a focus, a fixed point focus, and a distance from its line, a fixed line here at the bottom of the edge of the paper, is always the same value. Its distance from the focus, distance from the line is always the same, and out comes this beautiful U-shaped curve called a parabola. Is that quadratic? Is that one of these graphs in disguise? In fact, in the notes below, I've got a couple more examples of U-shaped graphs that appear in man-made world and natural world. We wonder, are they quadratic? So the real question is, how would we know? So I'm going to start off the next lesson with Galileo, what he thought about gravity and what led him to say that was quadratic. Because this is really cool stuff and will help us then play with other things that we're wondering about. You've got to love mathematics. This is cool stuff. So I'll see you next lesson.